So this is going to be the last of my 4 talks on topics in preparation for our spin geometry reading group. Um, as mentioned, we are starting it as of this week, and due next week we are going to read the first section of the first chapter of the book on Clifford algebras. If you care to read that section of the book, the things discussed in this talk aren't going to be directly relevant. They'll only start being relevant starting section 2, and similarly with the other talks, they are more about kind of later things that we'll see in the book. Nonetheless, I think this is a nice talk to give now in preparation. I mean, it'll be the recording that people can always watch back. So I'm going, yes, to talk about leaf theory, but actually for the majority of this talk, I will instead talk about topological groups instead of leaf groups. Now, my reasoning is that I kind of want to give an overview of the whole kind of hierarchy and kind of not full classification, there's none, but just kind of a big picture view of the groups and topological groups, because we all encounter a lot of examples, and really we won't explicitly use any leaf theory. We'll just kind of have it in the ambient background. And I think much more important than knowing the more technical notions and details is to have a fairly intimate understanding of just the concepts and how to like fit together. So the starting point of this talk will be the notion of a topological group, and specifically, I guess the starting point will be not the notion, but the theorem motivating it. So this is the definition of, well, this is not quite the definition, but it's essentially the definition of what an exponential function does. Um, this is one valid in the circle, so we have like uh, an, an imaginary exponential function, so to say. But if you replace the circle here with the um, reals, the non-zero reals on the multiplication, then you're going to recover the usual notion of exponential maps from uh, R to R. And that's the definition that Seibwaki used. And really there's something quite convenient in Fourier theory. It's actually, well, what this exactly says is that any continuous group homomorphism from the reals to the circle. So read this. We have the reals and the addition, which is a group, and the circle and the multiplication. You can view it in the complex plane. Then you have multiplication of complex numbers. And essentially, any such function, as long as it's continuous, that turns addition to multiplication is exponential. It's not difficult to prove if you just think about kind of sampling it on the dyadics, for example. So numbers which can be written as 1 over 2 to the n, or a sum of such numbers for some integer n. You'll notice that it has to kind of work square root-wise, and then you can piece it together by continuity. It's a fairly straightforward exercise. And this is like a fairly useful remark in Fourier analysis. It also allows one to generalize Fourier analytic methods to other contexts. And really, I put this here to kind of remark that, well, it is fruitful to try to connect algebraic notions and topological notions, not only in algebraic topological ways, where one starts with something topological and kind of completely essentially forgets the topology, just obtaining an algebraic object, but in a more algebraic way, where you start an algebraic object and kind of view it topologically. So you start with some group reals and addition, and you think of them as a topological object. So you also have topology. And in order to think of something algebraic as something topological, this is the subject of topological algebra, and for groups, you get the notion of topological groups. Now, a topological group is any group whose underlying set we also regard as a topological space, such that both the group law, the multiplication of the group, and the mapping an element to its inverse for the group law are continuous. Now, it's important to require both of them to be continuous. It's not too difficult to come up with examples where only one of them is continuous and the other isn't. I'll leave that as an exercise. Though there are contexts, such as for compact groups, or for when G is the topological manifold, where it actually follows that the mapping x to x inverse is continuous, provided the group law is. So that's our starting point. We have something which is both a group in topological space, and it's like that in well-compatible ways. And so, as with all mathematical objects, let's start this talk by looking at examples and kind of looking at general constructions. So clearly, Rn and Cn, so throughout this talk by lowercase k, I shall denote either R or C, as in you can choose any of those two at every single point in time when they write lowercase k. Rn and Cn on addition. There's already any conventional or way of viewing these as groups. And so whenever people speak of Rn as a group or as topological group, one usually means addition. Same for Cn. Those are topological groups. Addition is continuous. It's similarly to the theorem above, elementary analysis theorem. So we obtain topological groups this way. And we also obtain topological groups as GL and AK, for example. So all the individual n by n matrices. This lives inside the space of n by n matrices with entries in K, which is in bijection, and we can set it to be a homomorphism to induce a topological structure with Kn squared, which is kind of high-dimensional Euclidean space under the Euclidean topology. And as a subset of topological space, we get an induced subspace topology. And this way, this gives us a topology here. And similarly to verifying that addition is continuous on Kn, we can verify that here multiplication is continuous. And again, there's no really obvious overchoice of group law. And of course, also, the mapping a group to its inverse is continuous. This can be derived from noting that the inverse of not the group matrix, the inverse of a matrix is 1 over the determinant times the transponent of its adjugate matrix. And everything here happens in polynomial ways, and polynomials are continuous, and this is how you can verify this. Another example, more geometric example perhaps, if you don't think of these GLMKs as particularly geometric. I mean, they're open dense submanifolds of Kn squared, as we've discussed in the last talk, is S1, which, as mentioned, we can view on the multiplication of the complex plane, making it a group. This way it's also isomorphic to the reals modulo the integers, with an isomorphism given by mapping x to e to 2 pi ix. It's essentially the contents of the above theorem. So we can see the various kinds of algebraic structures that carry natural topologies. There are many more. Something that I'm not going to discuss in this talk, but for example, p-adic numbers and constructions of that form give us a very rich family of groups, also very important number theory. But first, we'll stick to more kind of topological in relation to smoothness groups. So all of these actually, the spaces here are topological manifolds. This is something we'll get to later in the talk. So some general constructions. Clearly, any subgroup of topological group is a topological group itself. We can just take the subspace topology and we'll have that a restriction of a continuous map is continuous, so we obtain a topological group as well. Similarly, any product of topological groups is a topological group. This is less, I mean, this is still straightforward to verify, but it's not immediately trivial. You just have to check that when you work with the product topology, by which I mean the Tikhonov topology, so as defined in my topology talk, the most coarse topology, such as all the projections are continuous. You can verify that in that case, continuity of multiplication, the map mapping an element to its inverse in all of the factors gives rise to continuity in the product. Now, this immediately gives us a family of examples of matrix groups. Any matrix groups with real or complex entries, by which I mean, in this case, a subgroup of G1K, is going to be a topological group as a subgroup of the topological group. And so some special linear groups, also matrices of determinant 1, orthogonal groups, also orthogonal matrices, the ones that have the transpose as the inverse, and special orthogonal groups, orthogonal matrices of determinant 1, all those can be seen to form topological groups. So that's another rich family of examples one obtains. Now, also we can do quotients of topological groups quite well. I mean, again, these are just general constructions. I'm just ensuring to put them here that we know that everything works fine and as expected. These ones are the most trickiest to check that they work out, but it's also quite straightforward. You just have to verify that, again, the operations are continuous when you carry down the operations to the quotient. And now you have to induce the topology by taking the quotient topology, which in this case is the finest topology, making the projection continuous. So with this, we get more examples of topological groups, as for example, PGLN, PSL, PAL, and PSO. In general, this P prefix standing short for projective refers to quotienting by all the diagonal matrices contained in your matrix group. So here I denoted by just modulo K star, but really by K star here I mean the span of K star times the identity matrix intersected with your matrix group, or in this case GLN. And so sometimes these will actually, for example, PSLN, this will just be SLN if the dimension is right, because there are no non-trivial diagonal matrices. At least no boring ones. No non-boring ones. But sometimes they give interesting groups. So that's one way of constructing topological groups. But actually, topological groups carry a lot of interesting structure that we can study. A lot of kind of questions to ask. And something that's useful to see in many applications is that also any finite group can be regarded as a topological group simply by owing it to the discrete topology. Indeed, we can see that, well, we can view any group as a discrete topological group simply by taking the discrete topology into the underlying set, and then we see that all the operations are continuous. So this way we can generalize all kind of conventional group theory to topological groups and try to ask the questions in greater generality. So this is what I was getting to a moment earlier. We can actually derive a lot of very nice topological properties from topological groups. So for example, the one I will talk about here, in order to make a little claim about finite groups in a moment, is that a group is Tikhonov, which just means that any point and closed set can be separated by a function, real valued bounded function mapping 1 to 0 to alpha to 1. It's also Hausdorff, precisely when it is Kolmogorov. Kolmogorov means that any two points are topologically distinguishable, which means that there exists an open set containing one or not the other. So the set of all the open sets containing the points, this mapping a point to the set of all of its neighborhoods is injective. We can figure out the points by knowing which open sets lie in. So it's a very strong kind of extension of separation properties we have for groups. Just by knowing the Kolmogorov, we get immediately this more strong separation. This actually turns out quite useful. This allows us to prove, for example, a very nice result about measurability of groups, which allows one to construct, for example, Haar measures. There's a very nice blog post by Terence Tower I will link later after the talk on the topic. But I'm not going to get into that here. I just want to, with this, illustrate kind of what it's like working with a topological group as a topological group and the nice properties one obtains. And like I mentioned, this will be useful in a second. So let's get into the proof. I just want to tell you how it goes. It's very simple, but I think kind of the first time I ever seen topological proof, just in general topology, about I think 5 years ago or so, really felt like a kind of new way of thinking about proofs. And in a way, this kind of carries over with also topological algebra proofs, because now you're not only working with topological notions and all algebraic notions, you work with both at the same time. It's also similar to functional analysis and topological vector space considerations, where you also do the same thing. And then you get a very kind of rich terminology and theory developed mostly by Grothendieck in terms of all of these concepts, and as you do with topological groups in relation. So for our proof, let's assume we have a topological group and it's Kolmogorov. We want to show that it's Hausdorff. I'm not going to show that it's Tikhonov. I'll leave that as an exercise. I mean, it's not quite straightforward. It's a bit harder than showing it's Hausdorff, but let me just show it that it's Hausdorff. It's going to be sufficient for what we'll get to in a moment. So how do we show that the topological space is Hausdorff? We take 2 points and we find disjoint open sets containing the one point and the other. But before we do that, let's just consider taking some point and the neutral element. Because, well, something you can note about topological groups, on a topological group, we've assumed that multiplication is continuous. So if we take any element of a topological group and consider scaling by the element on the left or on the right, that's going to be a continuous function. So the map which, given some element g of g, maps it to gx, where x is some fixed element of g, or xg. Just kind of by general topological properties, you can see that they are continuous. And so in particular, g inverse X, sorry, not G inverse X, but G mapping to GX inverse is also continuous. And so indeed, these aren't just continuous maps, they're homomorphisms. And we can exchange any 2 points, or sorry, not exchange, but we can map any point to any of via homomorphism. The group is a homogeneous topological space, as sometimes is said. And so if we want to show that given any 2 points, we can find disjoint open sets, we can just shift everything by this homeomorphism, mapping one of them to the neutral element, and it suffices to assume that one of them is a neutral element. So let's do that. So let's take some element that's of our group and not equal to 1, to the neutral element. Throughout the talk, I will denote groups multiplicatively, except when it's explicitly addition, and I'll use 1 for neutral elements. Then, if we have a neighborhood around 1, an open neighborhood, which doesn't contain G, then what we can do, we can make it smaller and consider such a neighborhood around 1 such that any 2 points within this neighborhood have the quotient not contained within, sorry, this should, okay, that's a typo, this should say contain, okay, okay, so let me fix this. This should say G not contained and AB inverse contained. So G contained. Okay. Sorry about that. But yeah, okay. So what we can do, we can again shift our situation to have the neutral element and our G. And for now, let's suppose that we have some open neighborhood of our neutral element. And what we can do, we can take a smaller neighborhood of that, such that any quotient of 2 elements in the small neighborhood is still in the neighborhood. Now, why we can do this is specifically because we've assumed that all operations are continuous. Because of that, we know that the mapping some elements of G, A and B to A divided by B, so by this I mean AB inverse, this map has to be continuous because it's just a composition of continuous maps, like stuff with products of topological spaces. In particular, we know that the preimage under this map of our neighborhood intersected with our neighborhood. It's going to contain 1, so it's going to be non-empty, and it's going to map into our neighborhood. So everything works fine. We can do that, and now for any for, now for this neighborhood, we can shift it by the element in our group and obtain that we have the neighborhood, let's call W as here, and its shifted version, GW. Now 1 is in W, so G is in GW. And so we have 2 open sets, one containing 1, one containing G. And it's nice to see that they are disjoint. They're open because homeomorphisms are open, and shifting by a element of our group is a homeomorphism. It's nice to say they're disjoint. Well, what way to see this is quite simple. If we suppose a common element, we would have some element which is in W with also G times something. And then we would have that dividing by that something we multiply G by will give us an element of the form AB inverse, which would have to be equal to G. But we know that we suppose AB inverse to be in W, so that's not the case. And because of that, any in-common elements give us contradictions, so they have to be disjoint. And well, yeah, in general, we can just shift. So just for X and Y, shift everything to the left by Y, for example, in the sense of multiplying on the right by Y inverse. And so this way we can kind of verify that it suffices to assume a being Kolmogorov to get a how to work. Now there are non-Kolmogorov topological groups, though some authors assume that all topological groups are housed off like Kolmogorov or Tikhonov. But really the only kind of non-trivial behavior one obtains topologically in those is kind of clumping of elements into these indistinguishable kind of clumps of elements. So I have an example, this example. So this is a topology on the client 4 group, which is the direct product of the cyclic group 42 itself. And we can just declare these blue sets to be the non-empty opens. And we verify it's continuous, just kind of explicitly. Sorry, it's topological, so the group law is continuous and the neutral element, sorry, the map mapping X to X is continuous. We can see that. And this is not going to be a Kolmogorov group because we have indistinguishable elements, these clumps. But whenever you have a non-Kolmogorov group, you can just take the Kolmogorov quotient identifying these clumps, and you end up with a Kolmogorov group, and it's going to be a Hausdorff and a Tikhonov group. In general, the Kolmogorov quotient of a topological space is just the quotient space you obtain by identifying indistinguishable elements. And it has a nice universal property. It is the initial Kolmogorov space you map into. And in the case of groups, you can verify that you have a normal subgroup you're quotienting by, and you result in a group. So in this case, you would get the cyclic group order 2. And now, in the case of finite groups, we know that a finite Kolmogorov group, as noted, is Hausdorff, and consequently points are closed, is Fréchet. And because of that, all points are closed, and so because there are finitely many of them, all subsets are closed. It's a finite union of closed subsets. And consequently, any finite Kolmogorov topological group is discrete, and any non-discrete finite group is one with a discrete Kolmogorov quotient, and it's just kind of a question of putting these clubs. I mean, it's combinatorially interesting how you can put these clubs, but fundamentally, it's just kind of this phenomenon that happens. So really, in the finite situation, we can recover all classical group theory by just taking discrete groups, and whatever's left over is kind of not particularly interesting, except if you care about the combinatorial way you can put these clumps together. Now, something interesting to note, though, is that we can try shifting to a more broader picture of non-finite groups to kind of detect more interesting topological groups, such as the examples we cared about. And, well, first of all, it's kind of useful to remark that the finite groups will be exactly the discrete compact groups, which is kind of a nice way of thinking about finiteness as discreteness plus compactness. But more interestingly, we can think of this clumping as a question of connected components or path components. Because you see, the connected components of a topological or a finite topological space will be exactly these clumps of elements. And well, okay, long as it's not something like a Sierpinski space, or let's say you have a finite topological group, will be exactly these sort of clumps of elements. The reason it can't get more complicated because of this exactly this homogeneity of our group, that we can just put any element in any other spot just by shifting everything properly. And the reason you can see this to be connecting components, in fact, equivalently path connected components, is that, well, you cannot write any of them as a disjoint union of open sets, and also a function out of any topological space into an indiscrete space, so a space where there are only two open sets, at most two, is going to be continuous because there's nothing to check for the preimages to be open. And so because of that, we have paths from the unit interval to our points, and in this way we get as our clumps for our Kolmogorov quotient the path components. And generally we can do the same thing for any topological group, but instead of caring about this weird kind of pathological case of topology, we can forget that, and for our infinite generalization, just care about the connectivity. So it's not difficult to verify that the connected component of the identity, also the path connected component, the path component of the identity, they are subgroups of our groups. In fact, they are normal subgroups, in fact, fully characteristic subgroups. Now, what does it mean to be fully characteristic for a subgroup of a group? We don't have to assume that our group is topological to define this notion. It just means that it's invariant under all, or when it's cut off, under all endomorphisms of the group. So if you think of a normal subgroup, it is a subgroup that's invariant under conjugation. But conjugation is just one kind of automorphism. If our group is invariant, our subgroup is invariant under all automorphisms of our ambient group is called characteristic, and on all endomorphisms fully characteristic. And of course, any fully characteristic group being invariant under all endomorphisms is invariant under conjugation, and so normal. The reason we get this very strong property of being fully characteristic for the path component of the neutral element is that we can verify that well, given any continuous, well, okay, it should be topologically fluid first because it's not quite properly spelled out. But given any continuous um, endomorphism, it's going to map the neutral element to itself because it's an endomorphism. And because it's continuous, it's going to map the connected component of the neutral element to the corresponding connected component, same with the path component. So you're going to obtain a map that maps the connected component to itself, and so we note that the connected component is closed on the multiplication. And same for taking multiplicative inverses as well. So we know that, and we know that it's closed on the endomorphisms. It's invariant endomorphisms. So this way we get this normal subgroup. We can also quotient and get a version of the Kolmogorov quotient, um, and kind of try to see how we can abstract away from the finite situation to kind of arbitrary topological group. So really, the reason I started off, I mean, for somebody who's purely interested in Lie groups, maybe it might seem a bit uh, unmotivated to start our discussion of like very geometric objects with obscure finite topological groups. But I feel like it's good to think of, again, kind of, I mean, I'm intending to give the broad picture. You have um, topological groups in mass, just all the possible topological groups, which kind of generalize finite groups, and of which Lie groups will be special examples of. And if you understand the structure of these and how, for example, finite groups fit into it, I think it gives a good overview to also think about Lie groups and the groups that we'll encounter in the uh, book. Yeah, something I've had kind of on my mind on and off the past few months is that I think it would be really nice to have a four uh, semester or four-part course about groups. And you can do general group theory in the first part of the course. And the second, you can do topological groups, and then move on to differential things, to Lie groups in the third. And as the fourth, you can also do algebraic groups, for example, which is kind of a fourth way of uh, looking at groups with additional structure that's very useful in modern mathematics. And it's kind of, it all builds up on each other. But yeah, I think that topological groups are something that comes before, and before those comes finite groups. So I think it's good to mention how they fit together. So yes, we can try to look at how connected components look like in arbitrary topological groups. So yeah, we get Kolmogorov quotients defined, and in general, given any topological group, we get a short exact sequence. We take a connected component of the identity or path component, doesn't really matter. I mean, in general, it'll be different, but we can do either. So topologically fully characteristic subgroup, or at least normal, let's say. And it embeds in our group, of course, because it's a subgroup. And then we can take the quotient, and we get this short exact sequence where the first group is uh, connected or path connected. The middle group is just an arbitrary group we started with, and the third group is totally disconnected, totally path disconnected. To be totally path disconnected means that no 2 points are joined by path. And that totally disconnected means that connected components are singletons. So really, this allows us to kind of split any group to some extent into a kind of connected component and a totally disconnected component. And also, often people will study either of those. Will mostly focus on studying connected groups, but you can also go into the totally disconnected realm of groups, which is kind of what I've mentioned with number theory and p-adic groups. You get so-called um, profinite groups, which are essentially the groups you can build out of finite groups by taking products of groups and taking, well, more generally taking limits of groups. Um, yeah, but I'm not going to go into that, but just this is kind of how the topological group theory uh, branch is organized in mathematics. You have the kind of classical path-connected things and the, or just connected things, and the kind of number theoretic, totally disconnected things. I mean, there's just one way of viewing it. I think that's kind of a nice perspective. So one example where we see this come into play. Actually, this is, I mean, it's a bit ironic given what I've said because this is the totally disconnected example. But just caring about the pure group structure, mostly these are like finite groups or maybe the integers and stuff like that. We can define the mapping class group of any sufficiently nice topological space. So one condition that suffices to be locally compact Hausdorff locally connected, which is kind of a mouthful. So you can also just work with topological manifolds, which are just zero manifolds. Locally compact Hausdorff means that it's Hausdorff and any open neighborhood around the point contains a compact neighborhood. And locally connected means that any point has, in any open neighborhood, a connected neighborhood. So given that, given such a nice space, we can consider all the homeomorphisms from our space to itself. And indeed, we can view this as a topological group in the so-called compact open topology. The way to do this is you consider all the as a kind of building block for open sets to generate our topology from, to take the smallest topology containing these. It's called a basis or a sub-basis. We take, given any compact in our space X and any opens in our space, we take a map which maps the compacts into the opens such that they intersect some given opens. It's a fairly technical construction that generalizes the topology one gets from considering the infinity norm in functional analysis. But we can do this in this context, also manifolds, and we get a topological group structure on the group of homeomorphisms from X to X. In general, we'll still get a topology, but it's not going to be a topological group structure. It's not trivial when it is, and when it's not. I'm not sure if it's classified. But then we have this topological group, and we can take the path component of the neutral element, and throughout this talk, I'll switch from notation, writing a subscript 0 or a superscript plus for the path component of the identity, or the component of the identity, the connect component of the identity, without, I mean, it's not correct that 0 refers to paths and plus refers to regular connectivity. It's just either refers to either. It's not really standardized notation, and I'll just use whatever is more common for the given thing. But taking this quotient, we get all the homeomorphisms, and we kind of take those homeomorphisms that are kind of in the same connected vicinity as doing nothing. We get this called mapping class group. And in fact, you can also characterize it differently. You can think of those either as diffeomorphisms that are in the same vicinity as the connected component, or you can think of those as identifying homomorphisms up to what's called isotopy, essentially just shifting them around. So it's actually a very visual thing, and I mean, it's a classical geometric topic. I think this, I'm not sure if this definition of the mapping class group is actually even the first one to ever appear. I think, pretty sure it's already been considered by people like Riemann and just kind of computed for surfaces and stuff like that. So you can prove a lot of things about computing it, and it's just kind of a common thing to consider in topology. But yeah, this is an example of something that's usually finite or not discrete because, well, it's under this topology, it's totally disconnected, totally back disconnected. So that's just one example of how kind of this construction. So, I mean, it's a motivation for why I talked about finite topological spaces and Kolmogorov quotients, because, well, why do we take these connecting components? Well, it's essentially an analogy. We start with classical groups, no topology whatsoever. We can extend this to big topological groups, and then in the classical case, we get these Kolmogorov quotients in a natural way, and in the infinite, it's pretty natural to instead move to connectivity. Now, that's one example of how we can apply this. We can also consider something else. We can, instead of considering path connectedness, we can define a so-called higher version of connectedness. And this is actually something that is going to be quite important for, at least in the one-dimensional case, for our reading. So I think it's good that we cover it now. And essentially what we do, you can realize that the space is path connected exactly when any given function from the endpoints of a closed unit interval extends the whole closed unit interval. And essentially, the closed unit interval is just one disk, which I write D1 here, and its endpoints to zero-dimensional S0, as I denoted here. If we just replace the superscripts with arbitrary dimension, we get a notion of n-connectivity. Now, zero connectivity, in that case, is path connectivity, or path connectedness, and one connectivity is then referred as being simply connected. So what this looks like is as the following. So here's an example of a not simply connected space, the torus. However, there are still examples of kind of one connected subspaces, in particular functions which extend. So in light green on the left, you can see we have a map from the circle, by which mean I have the circle and I've drawn the image of the circle under the map onto the torus, and kind of I just identify intuitively that's the map. And we can extend this to a map from the disk where we also map interior points of the disk into the circle. However, if we try doing this, for example, with the orange map as I've drawn on the right, it's not something you can do because, well, the torus in this case is it's the shell of a donut, so to say. It's the just a boundary. There's nothing inside, and you cannot fill in that space. Not a trivial thing to prove. It's kind of like the Jordan curve theorem, but it's something quite classical in algebraic topology. And so in this way, we see that it's not simply connected, this space. So just to be clear, the torus here, or in general, a torus refers to a power of a circle in the sense that you multiply the circle itself a bunch of times, and a circle is topological space, and so is the torus. And so we can talk about this notion of connectivity. However, what this example does illustrate is that despite not being simply connected, torus is locally simply connected. You see, if we take any point on the torus, we can find a neighborhood such that it basically looks flat. I mean, it's manifold. And that neighborhood is going to be simply connected. So any point that meets a simply connected open neighborhood. Actually, this should say arbitrary small simply connected open neighborhood. So in general, as mentioned, any topological manifold is locally simply connected. This should say locally simply connected. Sorry for the typos. It's a running theme for my talks. But yeah, any topological manifold is locally simply connected because topological manifolds are things that are locally Euclidean space, and Euclidean space is simply connected, so the locality carries through this way. And one thing one can attempt doing with locally simply connected spaces is to kind of untangle the non-simple connectedness. Specifically, there's this notion of a universal covering space, or universal cover of the topological space. That's just any fiber bundle who has this space as the base, and as the total space, one has a simply connected back-connected space, such that this fiber bundle is with discrete fibers. Now, as a corollary of this, of course, the image of a path-connected space in the continuous map is path-connected, so X, in order to admit a universal cover, needs to be path-connected. One can also verify that, well, one can see that actually X does not need to be locally simply connected, but being locally simply connected suffices. Actually, well, that's going to be the next slide. However, there's also a weak notion of being semi-locally simply connected. Well, it suffices assuming you assume also local path connectivity. So here's an example with the circle. The circle is not simply connected as the torus. It's just a one-dimensional torus. And well, we can take the identity map of the circle, and of course it doesn't lift to the disk, at least intuitively, of course. And we can untangle the circle if we just imagine that it's not a circle, it's actually kind of a giant spring that's been squished. And well, it's an infinitely long spring. We stretch it out, and it just the reals. And so we can realize the reals as this two-ways helix spiraling infinitely, and just map a real number t to cosinus t sinus t. So essentially just the value under the complex exponential. T maps to the it viewing S1 in the complex numbers. And this serves to give us a fiber bundle. Any point has a fiber of z, they're discrete, and this untangles the circle to a simply connected space because the reals are simply connected. Any point, any function from the circle can be extended to the disk because we'll have extreme, the circle is compact, so its image is going to be compact in R, so there's going to be a largest and least element. And then we can just map the disk between those elements, essentially. I mean, it's perhaps a fun exercise to prove that this works. But yeah. So in general, the conditions that suffice to require are yes, path connectivity and local path connectivity. Local path connectivity means that any point has in any open neighborhood a path connected open neighborhood. And if you assume these two, and you assume that the space is locally simply connected, and in fact one can weaken this condition a little bit to get the exact factorization. It needs to be semi-locally simply connected, which just means that the extensions may value not in the open neighborhood where it's local, but just the whole space. If you take these assumptions, then one can prove that there exists a universal cover. And in fact, not only a universal cover, a unique up to 5 bundle isomorphism universal cover. In fact, there's this universal property one can give. That's why it's called universal. It's the initial simply connected discrete fiber bundle, such that well, sorry, not the initial simply connected simple connectivity characteristic. It's the initial path connected. discrete fiber bundle over our space. So given any over, we have a unique fiber bundle morphism from the universal cover to it. So actually, this is very analogous to what one has in Galois theory, where you have some field extension, some Galois field extension. So for example, the algebraic closure of a perfect field, and you have the in-between extensions. And so the algebraic closure, say, is being algebraic closed, let's call being simply connected. And we get that we have these kind of in-between extensions, and we have also this universal property of kind of the algebraic closure extending any finite algebraic extension. In fact, if you think about things in terms of algebraic geometry, which also actually uses tools of topological group theory at times, these things are literally the same thing. So that's kind of a nice thing to remark, but we're not going to get into this. This would require a lot of technical machinery. It would be a field for this talk. So a useful thing to remark is that affects the properties of universal covers and covering spaces. So covering spaces are these discrete fiber bundles with path-connected base, path-connected total space, well, then also path-connected base. One can verify that the universal cover of a topological group is in a unique way a topological group itself. You simply, to multiply two elements, map them down. Well, you take paths. Okay, it's not, there's not a unique group law, but absolute isomorphism is a unique group law. You fix an element in your total space, in your universal color, then given any two elements, so this element is going to be the neutral element, given any two elements in your universal cover, take paths from the neutral element to them. The universal cover is path connected, so there are such paths. Then map them down to your base, which is the topological group by assumption, multiply them there, and then you can prove that there's a unique lift back to the universal cover, and wherever it lifts to, you can define to be the product. And in this way, you get a unique up to isomorphism group law. I mean, unique also up to just kind of shifting. Well, I guess it doesn't make literal sense to speak of shifting. It makes sense in the case of, well, intuitively you can think of it as shifting because, well, no, actually, it does make sense to define it formally as shifting because it's just a question of kind of given one group law, shifting everything to have some over element to be the neutral element, the neutral element. Yeah. So this way you get another plethora of topological groups, just universal covering groups from any given topological group. So I think at this point we're ready to move on to the differential situation and apply these concepts there. Again, kind of building up from the finite things to topological things to now smooth things. So yes, Lie groups are the differential situation. That's the name one uses. And they are essentially the same thing as topological groups, except our underlying space now is not a topological space, it's a smooth manifold. And conventionally, one speaks of real manifolds, always one specifically specify complex Lie groups. And one wishes to have the operations be not merely continuous, but also smooth. Both multiplication, the group law, and the map mapping X inverse. And actually, it's a very remarkable theorem. For a long time, it was an open problem, known as Hilbert's fifth problem. It suffices for the operations to be continuous, long as the underlying space of a topological group is a smooth manifold, then automatically your operations are smooth maps. You can verify that. So it's actually a very kind of straightforward way of verifying that things from manifolds. You just verify that the maps are in fact continuous. It suffices, which is a very strong claim, which wasn't trivial to prove, but it was proved around the 50s. And okay, with most of my talk so far, I've been keeping the exposition in a way that can mostly be kind of logically followed, implemented in Lean, so to say, just kind of derived by yourself. But in this talk, I'll mention some theorems which are kind of big kind of classification theorems and such, which you can't immediately derive, which need some more machinery, which I'm not going to develop. And so just kind of have to take my word, or I'll put some references at the end of the talk. But yeah, it's kind of different here. Just a big theorem, which I think is good to put into, yeah, give an overview of the kind of structure of all things happening. So immediately, as with topological groups, we have the same examples basically, because most of the examples I gave were Lie groups. The only example I gave that isn't is the Klein 4 group, where you have a weird topology in it. And so you take Rn, S1, GLNR, SLNR, ONR, SONR, anything. You can also take C here. You'll get, again, smooth manifolds and hence the groups, because you can verify that multi-maps are continuous at this smooth. Also, it's interesting to note, people don't realize, but finite groups still persist. Any finite group is a Lie group, just a discrete Lie group that's totally disconnected. So I guess if sometimes you might require manifolds to be connected, in that case they're no longer Lie groups, but in general for Lie groups people don't always assume them to be connected, so this way you get any finite group is a totally disconnected Lie group. In fact, you can verify that discrete finite groups are exactly the totally disconnected Lie groups. It's one and the same. So as with the topological situation, we have the path components, or also the connecting components of the identity. For manifolds, being path connected or connected is the same for open subsets. So we have those in Lie groups, and we can verify that they are Lie groups themselves. In fact, there's this stronger theorem known as Cartan's theorem. Those are different names. I think classically it's referred to as Cartan's theorem, but there are multiple theorems known as Cartan's theorem in Lie theory. Cartan did a lot of work. And it tells you that any closed subgroup of a Lie group is an embedded submanifold, and hence a Lie group. So in particular, we not only know that SLN is a Lie group because we know that SLN is a manifold, but because we know that it's a topological group and SLN is a subgroup of GLNR. SLNR is of GLNR. So actually, there's a very simple way of verifying that things are manifolds. If you know that GLNR is a manifold, you no longer have to worry about taking regular values and all that we did in our last talk. We can just verify we have a subgroup that gives us a manifold, which is a very convenient way of checking that things are Lie groups. Again, this is a fairly big theorem. I mean, it's much less technical to prove than the previous one. It can be done in an introductory Lie theory text, but I'm not going to develop the machinery to show this claim. I'm just going to have you take it to my factor, take it on Cartan's name. You can look up his paper. I think it's in English, I think, not necessarily German. Not sure. I'm sure there's an English translation. So also we can verify that if you take a universal covering space of a manifold, it's a manifold itself. This essentially follows because, well, if you think about the universal covering space, the fibers are discrete, so you kind of get these sheets, and every sheet locally gives you a homomorphism to the manifold, and so it's again locally equated. And in particular, you get that by our Hilbert's fifth theorem, or the theorem establishing the solution to Hilbert's fifth problem. It's also a Lie group if our base is a Lie group. So this way we get, again, the same constructions now in the case of Lie groups. And perhaps it might seem kind of lazy to just carry them over, but these constructions actually turn out to be very fundamental to a lot of kind of things one sees in practice, also with the groups you'll encounter. So there's going to be some examples coming up. Another one thing to note, which is different from the topological group case, is that any connected Lie group has a unique maximal compact subgroup, at least up to conjugation. This is known as the Cartan-Iwasawa-Malchev theorem. Again, Cartan making his mark. And in this way, we get this kind of way of giving a Lie group having all of these, not, I shouldn't say derived, because the derived group of a group is also a particular notion. It's the group generated by commutators, but you have these associated groups. So we can consider this example. Let's start with GLNR. We can, for example, take its path component of the identity, or it's a manifold, so, I mean, it's a Lie group, so also the neutral component of the identity, the connected component. And this gives us all the positive determinant real matrices of the same size as we started with GLNR with. That's also the motivation of why people write a plus, because we get a positive determinant here. Now, the maximal compact subgroup of GLNR is ONR, and of GLNR plus is SONR. Now, if we take, now we have this group, and we can take the universal cover of that, and the universal cover of SONR gives you the so-called spin groups, which are things that we are going to talk about in the book, except for n equals 2. For n equals 2, SO2R is just a circle, and then we get the real standard addition. But for n greater 2, we get these non-trivial groups. And for the orthogonal group, we get the pin groups, which themselves are the universal covers. Not the universal covers, they cover the spin groups. Yes. So, in general, we get this picture. We can start with any Lie group, and we can put it to be a connected Lie group if we just take the connected component of the identity. And out of that, I mean, these constructions apply to any Lie group except the maximal component, maximal compact subgroup. So that it needs to have finitely many connected components, which I mean works with most Lie groups, but still, it's kind of nice to think about connected Lie groups. And the universal kappa, it needs to start with a connected Lie group because we need to have a connected base. So we kind of, out of any given Lie group, can have all of these flowing out, and you can really get a lot of examples. I think like the main Lie groups, also the spin group, the whole topic of our book, really flows out of this structure, which also essentially holds true for the most part for topological groups. So there's a lot of rich theory that you can just get out of studying topological groups and then applying them to Lie groups. In fact, for example, Fourier analysis mentioned really can be done purely topologically as well. It's exactly the thing of mapping to a circle, and one obtains something known as Pontryagin duality, and you get on any sufficiently nice topological group as study of Lie theory, a study of Fourier analysis, Fourier theory. Rudin has a very excellent book called Fourier Analysis on Groups. That's exactly the topic that he studies in that book. So to put Lie groups into more tangible connection with things accessible to work with, there's a very useful way of associating linear algebraic objects to Lie groups. Because, well, if you think about it, in differential geometry, we study locally linear things, study smooth manifolds that locally look like Euclidean space, and we think of Euclidean space as a vector space, and we get these tangent spaces. We can try interpreting what we get under this linear correspondence for Lie groups. In fact, we get something interesting. We get so-called Lie algebras, which we'll get to in a moment. But in order to get to that, I need to tell you about a way of thinking about tangent vectors at a point in the manifold. I've not talked about it in my differential geometry book, but differential geometry text talk. But it's a quite convenient way of viewing them here. So when you have a tangent vector at a point and a smooth function defined, there's another type of this should say smooth functions modulo being equal in the neighborhood of the point. Many typos. But yeah, so let's say you have some point in a smooth manifold. Then if you have a tangent vector at the point and a smooth function defined in the neighborhood of the point, then we can define the directional derivative of the smooth function along the tangent vector point, which is just going to be a real number. So in classical analysis on Rn, you can take so the function is, in that case, Rn to R. You can take the gradient of the function, and you can take the scalar product with the unit vector in the direction, or with your tangent vector, it's going to scale. In general, you can characterize these directional derivatives by satisfying a version of the Leibniz property and by being just bilinear in your input functions. And so what I mean with there being a typo here, you need to ensure that two functions which agree in the neighborhood of the point give you the same derivative. Actually, sometimes it turns out to be equivalent, but I think there are examples where it's not, so it's best to ensure that this function only depends on your function locally around P, kind of as a condition to add. And indeed, you can verify that this gives you something if you consider all the directional derivatives, or sometimes they call point derivations at your point in your manifold. This collection comes with a family of canonical bijections, just one canonical bijection from the tangent space at your point to them. So if you think of the tangent space as in our previous talk of equivalence classes of curves, we can just compose the curve with our function, the neighborhood of our point, and take the derivative of that, valid at 0. The derivative here is just the classical derivative because our curve starts in R, maps to a manifold, and then we map back to R, so just a map out to R. And this only depends locally at that point because, well, derivative works that way from R to R. And so this way we get, for any tangent point, any tangent vector in our manifold that point a notion of directional derivative. To go the other way, you have to work a little bit. You can kind of allude to the basis you get with respect to any given chart. I'm not going to go through these details, and you can work it out for yourself. There are a lot of differential geometry books to it. I think in some of the references from my last week, the books cover the equivalents. So the reason it's useful for us here is specifically to linearize Lie groups. And the way we can do that is by defining the so-called Lie bracket of vector fields. So given two vector fields on our smooth manifold, any smooth manifold, we can define the Lie bracket by something that at first seems kind of arbitrary, but actually has quite nice intuition behind it. So let's say we have two vector fields v and w, and let's think of our tangent vectors as directional derivatives. So in order to define the Lie bracket of v and w as a vector field, we're going to have to define the directional derivative associated to a point, so the tangent vector at any given point for our Lie bracket. To do that, we suppose some smooth function on our neighborhood of a point, and we want to define what the directional derivative is. The way we do that, we have our v and w, and what we can do, we can get two functions. One function maps a point in our manifold to the directional derivative of our function with respect to w, and one the same with respect to v. So we get two smooth functions, and now these smooth functions we can use to take directional derivatives of them via the vector field. And essentially we get this construction. Now it's a very elaborate construction, and it's not immediately obvious that this is a directional derivative at all, but you can verify that it's indeed linear. It satisfies the Leibniz property, and it only depends on the functions locally. And the reason all this works out is this intuition you can work out. And in fact, indeed, there's a formal way of writing this out that requires a ton more machinery, which is why I didn't put it. But essentially, we can take the following picture. So let's consider S2. Let's take a point, and let's say we have two vector fields, V and W. Now, these vector fields are going to give us vectors, tangent vectors, at any given point of the manifold that they're on. In this case, our sphere. And what so we have to assume, for our purposes, they're smooth vector fields. And so yeah, whenever I was saying vector field, I meant smooth vector field, of course. When the points are nearby, the vector fields then also value closely. And what you can do, let's start on some point P, and let's try finding the value of the Lie bracket vector field of V and W. Essentially, what you can do is, because they are smooth, we can think of kind of them defining a flow, what's called, on our manifold. What that means is that we can define this function, or this family of functions phi t, but t is a real number, which maps any point to where it would be if we imagine the vector field to be like a fluid, and the point would be moving along the fluid. So formally, it has to satisfy some differential equations you can write out. You want that the differential of the flow corresponds to the vector field. And you also want it to satisfy the so-called semi-group property, which you can verify works out. So this is a question of dynamics, if you want to do it properly. So you can imagine just your point kind of flowing along the vector field, which is this function, the flow. And so in order to get the commutator, fix some time t, then flow along v for t, flow along w for t, then flow backwards where you've ended up along v, and then backwards along w. And because the vector field changes when you flow a bit, you're going to flow backwards a bit differently. Well, unless you don't, it depends, but this is a possibility. And you have to, I mean, this becomes kind of technical, but you have to consider this as like at minimal time. And because you pick up kind of a factor of t 2 times when you flow, you have to take the second derivative, and because you do it back and forth, you have to divide by 2. And this is the formal expression you get. But intuitively, essentially what you're doing is what's in the picture. You're flowing along one vector field, then the other, then backwards along the first, and then backwards along the other. And you do this kind of infinitesimally, and this gives you your Lie bracket. And so this way, you can do this at any point. It gives you a smooth vector field once more. So this immediately has some obvious properties. If you flow along V and then W and then backwards V and backwards W, same thing as the opposite of flowing along W, then V, then backwards along W, backwards along V. Well, at least infinitesimally. And also this is clearly bilinear. If you scale all your vectors, everything's going to get scaled. And you can verify this kind of scary looking, it's called Jacobi identity. One way to memorize this is not in this form, but you can remember that if you fix the brackets in place and permute in a cycle the three letters that you, or like the three entries you have, then sum everything up, then you're going to get 0. And kind of intuitively how you work with this is whenever you have the Lie bracket on 2 elements, and then you have some third element you take into Lie bracket of the Lie bracket, you can carry over this double Lie bracket into Lie brackets which don't use those 2 elements specifically. So it can be useful with computations you do with the Lie bracket. But this kind of immediately shows that the Lie bracket is really a very linear algebraic object. I mean, it's not difficult to verify that all the vector fields on your space give you a highly dimensional, infinitely dimensional vector space, and indeed you get this bilinear map there, you get an algebra structure. And in general, you can abstract this away and get the notion of the Lie algebra on a field, over a field. A Lie algebra over a field is just any vector space by any algebra, so vector space and multiplication, satisfying the same properties as the Lie bracket for vector fields. So those being, as mentioned, they have to be alternating. So if you flow, well, alternating means in this case that the Lie bracket of a vector with itself is 0, or vector field in the case of vector vectors are vector fields, sort of this physicist vectors. And this can be seen to, in characteristic not to 2, be equivalent to the condition that VW and WV map to additive inverses. And really, even in characteristic 2, this still follows, except just not the converse. And we want it to also satisfy the Jacobi identity. It's kind of the replacement of associativity. So Lie algebras, a very important example for us of non-associative algebras, like I think it's like the canonical example of non-associative algebras one comes up with. And conventionally, one writes in fractal letters like this. Like, yeah, I've never figured out how to write these on paper. That's how one commonly denotes it. But yeah, so that's what the Lie algebra is. And immediately we see that given any smooth manifold, we can take all the vector fields on it as the vector space and define a Lie algebra structure that is going to be an infinite dimensional Lie algebra. That's a bit big to study. So what one tries to do is get small Lie algebras, but before let me quickly make a remark of base change. There's another type, but this is a complexification, not complexification. There's an F missing. If you have a field extension and some Lie algebra over the smaller field, you can tensor it with the bigger field as the vector space over the smaller, where scaling is multiplication, and define a algebra structure like this. This is a general way of defining algebra structures and tensor products. And that makes the tensor product into a Lie algebra with a bigger field. And doing this when you tensor over a bigger field is called as base, is known as base change. And yeah, when you are going from R to Z, this is known as complexification. So given a real Lie algebra, you get a complex Lie algebra. And yeah, usually when speaking of Lie algebras, one assumes unless specified otherwise that they are real. So this gives you a way of kind of interchanging real and complex Lie algebra, at least going upwards. A very rich family of examples of Lie algebras one gets is if one kind of looks at the definition of the Lie bracket and just sees in every form, whether it's flows or derivations, that we basically just do things one way and then undo them. Essentially, it corresponds to this operation in associative algebra where we take 2 elements, we multiply them one way, and subtract them, multiply them in the opposite order. And given any associative algebra, defining this gives us a Lie algebra structure on the underlying vector space. So any associative algebra gives us a Lie algebra structure. So one thing one notes is that if the algebra subset is commutative, then the Lie brackets of this form are all going to be 0 and was going to get what's known as an abelian Lie algebra. So Lie algebra is abelian whenever the Lie bracket is constantly 0. It's not something you usually see with interesting algebraic structures, but for Lie algebras, being trivial means that literally the product is equal to 0 all the time. You can see that all the properties one assumes are satisfied. You have that the map is alternating, bilinear, and the Jacobian is satisfied because you don't have any constants you're adding. You can't do that because you're in a vector space. So yeah. Now, a non-trivial example one can obtain, for example, in dimension 2. You can verify that all one-dimensional algebras are abelian. It's quite straightforward because take any base element, you know that it has to multiply with itself to be 0 because the algebra is alternating. That already shows you that the product of any two multiples of your base element is 0, which is exactly the product of any two elements of the algebra. In dimension 2, however, you get a non-trivial algebra, exactly one. So one abelian and one non-abelian. And it can be realized in this form. We take all these matrices. This gives you a subalgebra of 2 by 2 matrices over F. And interpreting that as Lie algebra, you get a Lie algebra, which is not abelian. And you can see that those are the only two Lie algebras just by thinking about all the possible kind of values the Lie bracket of the two generators in the basis could give you. It's kind of a direct computation. It can be kind of fun. You can indeed enumerate any finite dimensional Lie algebras this way for any dimension. So it's kind of a fun thing to do. So you get these two-dimensional ones. And indeed, there's a very geometric interpretation of this. And to see that, we want to put these finite dimensional Lie algebras in the context of what we've developed with groups, Lie theory, Lie groups. So what we can do, instead of working with the whole collection of all smooth vector fields in a smooth manifold, which is a giant high-dimensional, infinite dimensional Lie algebra, you can start with a Lie group, and then given any one tangent vector, you can translate it to any other point in your group, any other tangent space. The way you do that, well, given our Lie group, we have these scalings. Because our multiplication is smooth, they are smooth, so we can take the differential, which is a map onto tangent spaces. So essentially, we can scale, like shift. I shouldn't call them. I mean, they are scaling. Better think of them as shifting. You can shift any tangent vector using some element to any other tangent space to be based at any other point. And so, given any tangent vector at the identity of your group, you can shift it to be anywhere else, and this gives you a smooth vector field on your group. Such smooth vector fields are known as G equivariant vector fields, and you can see that it's actually it doesn't matter if you work with left shifting or right shifting. So this way, you get for any tangent vector at the identity of your group a vector field on your whole Lie group. And using the Lie bracket of vector fields, you can get a vector field for any you can get two vector fields for any two groups for any two vectors tangent to the identity of your group. You can take the Lie bracket and then take the value of the resulting vector field at the identity, which essentially just gives you a operation, a multiplication on the tangent space at the identity of your group. And this way, it makes it into Lie algebra. Now, no, it doesn't really matter which tangent space you work with because you can identify them all just with the differentials. You can see that they're all isomorphisms because the differential of a diffeomorphism is an isomorphism. And just like with topological groups, shifting because of inverses gives you diffeomorphisms. And so you get this multiplication on your tangent spaces, and yeah, they turn out to be Lie algebras. And they are indeed finite dimensional Lie algebras because we know that tangent spaces of a manifold are of the same dimension as the manifold. And so we know that the dimension of the Lie algebra we obtain is that of the corresponding Lie group. So this gives us a construction of a Lie algebra of the same dimension as any given Lie group from a Lie group. And this Lie construction. And it's really a very useful thing. You can also do it on morphisms. So which means it's a functor. If you like this sort of language. If you have any smooth group homomorphisms, it's the right notion of morphism in this case of Lie groups, then, well, you take its differential, it gives you a map of the tangent spaces, and it's pretty straightforward to see that that's a Lie group, a Lie algebra homomorphism. So algebra homomorphism, it preserves this bracket construction. It's just a computation you can do in one line. An important family of these values of the Lie construction on smooth group homomorphisms is when you have the same target as source group, same domain and codomain, and the homomorphism you consider is conjugating by some element of your group. These conjugations are also referred to as adjugate maps in Lie theory, and when you take the differential, you get adjugate maps on your Lie algebra. And this way you have your group acting on your Lie algebra. So yeah, also similarly to Hilbert's fifth problem, it's actually quite a lot easier to verify this than Hilbert's fifth problem. Any continuous group homomorphism of Lie groups is smooth. I don't think we have the technology, the machinery to have this be an exercise, but it's a fairly straightforward thing to show. So yes, as mentioned, we have the same dimension, so we get low-dimensional Lie algebras, and you can, in the example of Rn, for example, compute it to be abelian quite straightforwardly, because, well, let's take some tangent vector at the neutral element of Rn, so at 0, and let's shift it everywhere. Essentially, what you get is just one of n possibilities, sorry, one of n-dimensional possibilities, and these possibilities correspond to, well, sort of like diagonal matrices. Perhaps not exactly the best intuition. If you think about it in terms of the flows, if you flow along one vector, and then another, and then back to the first, and then back to other, if you just shifted everything in Rn, you're just adding the vectors, just like kind of physicist vectors, arrows, sort of calculus, and then you get 0 when you take the Lie bracket of any two vectors. So because of that, you see that the Lie algebra of Rn just gives you an abelian Lie algebra. Now, more interestingly, if you work with invertible matrices, you get the Lie algebra associated with the associative algebra of all matrices. And this is very, very useful if you want to compute more examples of Lie algebras, because once you know this, thanks to properties of the Lie construction, whenever you have a subgroup of G and R, you can actually think about it as a sub-Lie algebra of this. And there's some technical things you can do to actually compute it explicitly using the exponential kind of an analogy with what the talk started with. In this case, it's going to be the matrix exponential. And actually, you can define exponentials on any Lie group, but I didn't get to this in this talk, I think. In order to do that properly, I would have had to talk about some more technical things, differential geometry. But you can find this in most Lie, in any Lie theory books. This is very fundamental for most explicit computations. So the way you actually do this correspondence of sub-Lie algebras of matrices from the subgroups of G and R is by one of the, I think it's fair to say, the most fundamental theorem in Lie theory. And well, the way that it was originally formulated, it's 3 theorems by Lie. That's why the name, I mean, it's not only the reason that they call Lie groups now Sophus Lie at the end of the 19th century, generated a lot of work on the subject of groups with a differential structure, now called Lie groups. But we get this theorem that he proved that really characterizes the nature of Lie groups quite well. And namely, it's a theorem that this map, Lie, if you interpret it as a functor between categories, and I'm going to explain what this means in a second if you're uncomfortable with this language, if you interpret it as a functor from the category of simply connected Lie groups to the category of fine-dimensional Lie algebras, then it is an equivalence. So note that you can take the Lie algebra of a Lie group that's not simply connected. Though it's not going to matter if you have a not simply connected Lie group, you can take the universal cover, and it's going to turn out that the Lie algebra of the universal cover is going to be the same as the Lie group you started with, because it's kind of Lie groups. The construction of the Lie algebra only depends locally on this bracket, and so it works out as long as you have local isomorphism. So this essentially means that you can think of simply connected Lie groups exactly as corresponding Lie algebras. And so for people now uninitiated with category theory, what this means is that to every simply connected Lie group, the bijectively corresponds a unique fine-dimensional Lie algebra and vice versa. And for, given what we've developed already, this is not part of this theorem, but this is just a corollary of the structure of things. For any non-simply connected Lie group, just move to its universal covering group, take the Lie algebra construction there, and you get this correspondence. And the way to understand how you move up is kind of related to this Galois correspondence I talked about earlier. So having this in mind, we can think about the example we had earlier. Oh, there's a typo. This should say, oh no, that's right. No, this is a typo. This should say the 0 should be in the lower corner. Actually, I don't think it matters. Yeah, I think this should be fine even though it's a typo. I thought to write the yeah, that's fine. So if you think about our classification of two-dimensional Lie algebras, we know that by Lie's theorem, they correspond to simply connected two-dimensional Lie groups. And by Lie's theorem, we already know that they're exactly two optimorphism simply connected two-dimensional Lie groups, because they correspond to two-dimensional Lie algebras. The Lie algebras are of the same dimension as the Lie groups mentioned. And we've classified just by working with bases, you can see there are two. Now, the abelian Lie algebra one gets, of course, if one starts with R2. That was our discussion on the previous page. But if you want to get this over one, where you have this kind of half filled in matrix on the first column, you can start with this Lie group. You take all of these matrices, it's a simply connected Lie group, and its Lie algebra turns out to be exactly that Lie algebra. And really, if you want to get into more serious development of the theory, this is where you anchor whenever studying Lie groups, think about them in terms of the corresponding Lie algebras, and that's a very useful tool. You can classify a lot of Lie groups this way. You can classify first Lie algebras using just purely linear algebraic methods, which is a very rich subject with very nice theory. Because I mean, it's just linear algebra. And then you can translate that to Lie groups and give some very useful results. But it's not something I'll cover in this talk. This is the end of my talk. I mostly intend this talk to just give you an overview of all of these notions. I mean, I think this is pretty theory. I did mention that this is supposed to be like a redeeming talk for all of the definitions I've been giving in my previous talks. I think it's very nice narrative. You start with classical finite groups. You can add the topological structure and abstract them away. And then if you add smooth structure, it abstracts away more generally, and you get all of these nice correspondences, notions you've seen previously on the lower level of notion of group translate into higher levels. I mean, it's not quite abstraction because topological groups are more general than Lie groups, but I think the narrative carries through quite nicely if you want to actually work with these things. But yeah, and well, we won't need any explicit Lie group computations in the book. I think we'll just use the aggregate maps a little bit, and that's mostly it. But I think it's good to keep in mind how all of these groups laid, like specifically this one diagram I drew with the connected components and the maximal compact subgroups and universal covering groups. I think that's really something I want to get across with this talk. I think this is really what gives a clear picture view of what's going on. So lastly, if you care about, oh, I don't know what that is. If you care about looking into this topic more, for general topological groups, I recommend this book by Arhangelsky and Tkachenko. It is called Topological Groups and Related Structures, and it's not only topological groups, it's also other topological structures, but it covers a lot of nice things, like the proof that Kolmogorov groups Hausdorff is going to prove you that Tikhonov, and it's going to prove a lot of these sort of nice results. For a very accessible and elementary treatment of Lie theory, I think everybody in this talk is familiar with this book. It's Lie groups, the algebras and positions by Brainsy Hall. And well, this was the first time I've ever seen the subject. And it puts it very accessibly. It talks about matrix Lie groups first and foremost. I mean, most Lie groups can be represented as matrices in the formal sense. You can define that. Though there are also some which you cannot. But Hall, he kind of gives you a very nice computational point of view to actually get your hands dirty and work things out. But if you care about a more kind of theoretical and kind of clean development of the theory, more into the spirit of what I've been doing here, but in a more differential way, you can take a look at this book. It's pretty recent, I think 2012, by Hilgert and Neep, Structure and Geometry Groups. It's a pretty long book. I think it's like 800 pages. Develops like all of the relevant. I think it even proves Hilbert's fifth and all that. So yeah, thank you for your attention. If there are any questions, now is the time to ask.
I did want to ask, and it may not actually come up in the book because it isn't just one thing, but the fundamental forces have this one symmetry group that's like
Yeah,
SU3
yeah,
cross SU2
SU2
cross
cross
U1.
U1. Yeah, the lead group.
Yeah. Does that have any particular structure to it that we should learn?
Not that I know. Well, I'm not. I, as probably is evident from the talk, I'm not the most theoretically familiar person. Mostly spent the talk talking about things adjacent to leaf theory, but I think that give you the right. I mean, the book itself isn't about leaf theory either, so it's more about just knowing the things on about leaf theory.
Yes.
So I don't know. I wouldn't imagine so. I think it probably just comes out because of very specific physical considerations. I mean, of course, you can give it characterization that it's exactly the group that pops out of the physical considerations, but I believe it's just kind of a coincidence. But maybe somebody else has more to say about that. But I don't know. I shouldn't be speaking about that.
Got it. No, it's fine. I think it actually might not even come up in just spin geometry purely.
Yeah, I don't think so. I mean, well, we'll see the special unitary groups and all that, but I don't think we'll. I mean, this is a very specific product of them. I mean,
Yes.
it comes from like the symmetries you have. So I guess that's why it matters. And so I guess it's a question like, why is it exactly those symmetries you have? Which I don't know. That's physics. Physics and leaf theory that I'm not familiar with. Okay. Any other questions before I end the recording?
Didn't you mention some posts from Terrence Tao?
Oh yeah, I can show that. Well, I'll show that after the recording.
All right.
Any questions about like the contents of the talk? Yeah, that's a lot of. I apologize with my over talks. Never believe what I say. Always think for yourself. There are typos and errors and stuff. Sometimes I write one thing and say another thing. I mean what I say, not what I type. But even what I say might contain subtle errors. So this, for example.
I think one thing at the very beginning,
Yeah.
We talked about turning multiplication into addition. Which direction is that going with respect to the like exponential map and the
Addition in the
logarithm?
Domain. So addition into domain, multiplication into codomain.
Okay.
E to the a plus b is e to the a times e to the b.
E to the a plus
The
b equals e to the a times e to the b. Yep. Okay.
A inverse or local inverse to this.
Yes.
Yeah. So if you again replace S1 with the positive reals, then you get isomorphisms and the inverse is logarithms, or no, as logarithmic functions. No, logarithms is straight because logarithmic functions are ones you can build out of them. Yeah.
Then I always screw up the direction, but I think there's an additional theorem that relates Lie algebras and the Lie groups with that.
With exponential maps? I mean,
yeah, it's like the log of.
Well, I mean, yeah, there's a lot of. I mean, this is what I didn't get into. Like here, if you want to actually do these computations, or with some of these theorems, if you want to prove them, you have a notion of an exponential on the Lie group, of the exponential on the Lie group, which takes a tangent vector. It goes from the Lie algebra to the Lie group. It takes a tangent vector in the Lie algebra, and it lets you flow along the tangent vector starting from the point you are exponentiating in the direction of the tangent vector for 1 unit of time along the flow of the like equivariant vector field you get from the vector. And wherever you end up is the value of the exponential. And you can check that it has some very nice properties, long as in your domain you have commuting, I mean the Lie bracket is 0 elements of your Lie algebra. It's a homomorphism, and that generalizes the homomorphism you have usually. And for matrices, you get the matrix exponential, where you go from the Lie algebra of G on R So by matrices to GLNR. And there you have you have a logarithm in the backwards direction, but it only works locally in general. It's never an isomorphism. I don't remember the conditions when it is. But you have like, you can explicitly do like an open ball of some radius and like whatever norm and get the inverse that way.
Yeah, cool, thanks.
Okay. Well, yeah, okay, I think I'll end the recording here. We can always discuss more after it.